Now this video is not actually going to start the lesson. It's just a little bit of a primer to help you bridge the gap for what you're about to see. So let's talk about what we're going to learn first. And yes, I got a haircut. So in this lesson, we're going to learn how to identify sigma and pi bonds in compounds. It's actually pretty simple. The act of doing it is pretty simple, but the theory behind it is a little bit complex. We're going to be able to state hybridization of the orbitals around a specific atom, which leads us to the problem of, well, what is an orbital? Now, in CP, we left orbitals in most classes as just sort of a statement that we'd refer to when we're writing an electron configuration. We'd say that this was the 1s orbital, right? And this is the 2s orbital. And clearly the 2p orbital has 3 electrons in it, right? The 3 means there's 3 electrons. So we'd always say that those 3 electrons are in a 2p orbital. But we didn't really, at least in my class, spend a lot of time clarifying what an orbital is. And in order to understand what hybrid orbitals are, we need to do a little bit of laying the groundwork. So let's do that. Now, you know an electron configuration is shorthand for a filling diagram, right? Sometimes these go horizontally more than vertically, but the idea here is the 2 electrons in the 1s orbital, you know they have opposite spins as they're spinning. That's what the arrows indicate. And of course, the 2p orbitals are higher in energy than the 1s orbitals. So it's a different way of representing an electron configuration, but we still haven't really defined what an orbital is. It's not just a line in a filling diagram, but clearly it indicates an area where electrons exist. So let's look at this a little bit closer. What is a 1s orbital or a 2s orbital? Well, an orbital is a region in space where up to 2 electrons can exist. Now I think that makes sense because we know that these little lines can hold 2 electrons on them. But what we mean by that is if you imagine that you had 2 electrons in this 2s orbital right here, those 2 electrons, if you took a picture of it, it might be right here at one moment, and then right there at another moment, and then there in another moment. So what this diagram is representing is not like thousands of electrons. It's representing a time-lapse capture of just 2 electrons, or maybe even 1, right? But no more than 2. So there's not 1,000 electrons in here, but you'll see after a while, you start to notice that this area that these electrons can be in around the nucleus in an s orbital is very spherical. Did you know that's what the S stands for? Except for it's in German, so a little bit of fudging there. But in any case, yeah, it's a spherical shape that those electrons can take on. Now the p electrons, the orbitals that they take on, the reason they're p electrons is because when you sit there and watch the 1 electron or the 2 electrons and you take pictures over time, the nucleus is right here in the middle. And you'll notice the electrons can't just be everywhere like they can be in an s orbital. They can only be in very specific places to the left or to the right of that nucleus. And after a while, if you take enough time-lapse pictures of it, you'll start to see that it takes on a propeller shape. That's what the P stands for, with a little bit of fudging. But yes, that's the idea. Right? It's the shape of the area that the electron is going to be in. Now you can see that s orbitals, there's only ever 1. But p orbitals, there are 3. And the reason is because those p electrons, like this one right here, can be above and below the nucleus. Whereas that one can be to the left and to the right of the nucleus. And this one can be in front of or behind the nucleus. This is referred to as the 2py orbital, the 2px orbital, and the 2pz orbital. The reason p orbitals have directionality is because they're not round. Like a round thing like a spherical one, you can just rotate it and it always looks the same. But a propeller, you can't, right? If you turn it on its side, it looks a little different. And that's why there are 3 p orbitals. But each one of these areas can only hold up to 2 electrons. So these are what orbitals are, is they're regions in space where we think there's a good chance of an electron being, and they happen to take on shapes. Now you might start to wonder, okay, well what do d orbitals look like? Where can d electrons go? Or even f for that matter. Let me show you. Oh, wait a minute, before we go into that, one other thing. What's the difference between a 1s orbital and a 2s orbital? Well, if the nucleus is in the middle, 1s electrons, like these two, just can't go as far away from the nucleus as 2s electrons. So it's kind of like Bohr's ring model, but not exactly, because not only can they be pretty far out, but they can be really darn close to the nucleus. What's the difference between a 2p orbital and a 3p orbital? Well, 3p orbital, it still looks like a propeller. It just has a further sort of range out from the nucleus that those electrons can go. So think of these as kind of like, these are pens for the, if the electrons are cows, these are pens to keep them in there. Okay? And there's not thousands, there's just two. So here is sort of the summary of the orbitals. S's are sphericals, P's are propellers, and they have X, Y, Z. That's why there are three of them. And you know that d orbitals, P's may have three orbitals, but D's have five. And these are the five shapes. Now, what we're saying here is, right here, look at this one that looks kind of like a clover leaf. There's not like 4 electrons. You can still only have 2 electrons, and the nucleus is right in the middle. The electrons can be in that region, that region, that region, or that region, but nowhere else. So those are the 5 d orbitals. If you're interested in knowing how these orbitals were discovered, it's a very mathematical process. The Schrödinger equation is what predicted these orbitals. But in any case, I wanted you to have that primer about what an atomic orbital is before we go into talking about hybrid orbitals. All right, now let's get to the lesson where we learn about sigma and pi bonds and how hybrid orbitals are formed.